Problem 5. How many subsets of 2, 3, 4, 5, 6, 7, 8, 9 contain at least one prime number? So first of all, how do we determine the number of subsets available? Well, consider every number. What is the probability that each number is existent within a subset of any given length? Well, let's consider the examples of 2, 3, 4, and 5. 2 can either exist or not exist within a given set. So there's two possibilities for 2. The same goes for 3, the same goes for 4, the same goes for 5, and etc., all the way until 9. We have two possibilities for them existing. Now, to demonstrate this fact, consider this subset, 3, 4, right? And then consider the subset 2, 3, 4. Consider 2 within these two subsets, right? What is the probability, what is the number of outcomes for 2 to exist within this subset? Well, the answer is 1, right? The only one possible way for 2 to exist within this subset is for it to not exist within a subset. So that's 1. But then consider the subset of 2, 3, 4. The subset of 2, 3, 4 contains 2. So what is the only one possible way for 2 to exist? Well, the only way for it to exist is for it to be present within the subset. So this possibility accounts for the fact that 2 does not exist, and this probability accounts for the fact that 2 does exist, which is why you have two cases of them existing within a given subset for each number. Now that we have this out the way, how many subsets do we have? Well, if every number has two ways of existing within any given subset, we have 2 to the 8 possible sets, because 2 to the 8 represents the number of possibilities for each number to exist within any given set. Now, how do I find the number of subsets that contain at least one prime number? Well, how many prime numbers are there? Well, there's 2, 3, 5, and 7. So consider how difficult it would be if I were to just do direct counting. I could have a subset that's 2, 3, but then I can have another subset that's 3, 2. They both are the same subset, so I have to divide by 2. But then consider the even more complicated case where I have 2, 3, 5. Right? If I have 2, 3, 5, I can have 3, 2, 5, 5, 2, 3, etc., etc. There's going to be so many overlaps that it's not worth the effort. We might as well just do complementary counting, where we count the total number of cases and subtract the number of cases that we do not want to get the cases that we do want. So how many cases, right, do not contain at least one prime number? Well, consider what this phrase means. If a subset does not contain a prime number. If a subset does not contain a prime number, there's only one possible way for each prime number to exist, which is to say that they don't exist. So there's only one, and one possibility for each prime number to exist within the given subsets that we don't want because they cannot exist. So there's only one way for them to exist. But the other numbers, such as, for example, 4, 6, 8, and 9, well, they can exist or not exist. We don't really care. All we care about is the primes not exist. Whether or not these non-prime numbers exist, well, that's a matter of choice. So therefore, we have two possibilities for each. So if we multiply everything out, we get 2 to the 4. So what is 2 to the 8 minus 2 to the 4? Well, one number that everyone should know is 2 to the 10. 2 to the 10 is equal to 1024. But let's suppose that you do not know this. How do we solve it efficiently? Well, let's consider 2 to the 8. 2 to the 8 is 2 to the 4th times 2 to the 4th minus 2 to the 4th. Factor out 2 to the 4th. That becomes 2 to the 4th times 2 to the 4th minus 1. What is 2 to the 4th? Well, that's just equal to 16. So that's 16 times 15. Now, what is 15? 15 is equal to 16 minus 1. So what is this expression? Well, 16 squared is equal to 256 minus 16. That gives me 240. 16, just to make sure, 96, 16, 256 minus 16 gives 240 indeed. So your final answer would be answer choice D. Always use arithmetic manipulation to solve it easier.